Foundations of Civil Engineering. Building the World from the Ground Up.
Page 1. What is civil engineering? Civil engineering is the art and science of designing and building the world around us. It's what makes bridges stand tall, roads smooth, and buildings safe to live in. Think about your day. The roads you drive on, the buildings you enter, and even the water you drink. All of these are possible because of civil engineering. At its core, civil engineering is about solving problems. How do you make a bridge strong enough to hold hundreds of cars every day? How do you build a skyscraper that won't sway too much in the wind? Civil engineers answer these questions by using math, science, and creativity. But it's not just about making things look good. Civil engineers also make sure their designs are safe, cost-effective, and environmentally friendly. Whether it's a simple sidewalk or a massive dam, every project starts with careful planning and ends with something that improves people's lives. In this audiobook, we'll explore everything civil engineers do, from the materials they use, like steel and concrete, to the powerful tools they work with, like AutoCAD and Revit. By the end, you'll understand how civil engineers help shape the world, and maybe even feel inspired to build something amazing yourself. Page 2. The history of civil engineering. Civil engineering is one of the oldest professions in human history. Thousands of years ago, long before the term civil engineering existed, people were already building things to make life better. Let's take a quick trip back in time to see how it all began. The earliest civil engineers built for survival. Think about it. Humans needed shelter to protect themselves from the weather and wild animals. Over time, they learned how to stack stones, shape wood, and dig into the earth to create homes, walls, and pathways. One of the first great civil engineering achievements was the pyramids of Egypt, built over 4,000 years ago. These massive structures required careful planning, teamwork, and knowledge of materials. Even today, engineers marvel at how ancient Egyptians transported those giant stones without modern tools. Later, the Romans took civil engineering to the next level. They built roads, aqueducts, and bridges that are still standing today. Their secret? Materials like concrete and an understanding of arches, which distribute weight evenly and make structures stronger. Fast forward to the modern era, and civil engineering became its own profession in the 18th century. As cities grew, engineers were needed to design safe and efficient buildings, roads, and water systems. Today, civil engineers use cutting-edge technology, but the goal remains the same: to build things that improve life for everyone. Every project you see today, from a towering skyscraper to a simple park bench, owes something to the long history of civil engineering. Understanding where we came from is the first step in appreciating where we're going. Page 3. The key branches of civil engineering. Civil engineering is like a big tree with many branches. Each branch focuses on a specific part of building and improving the world around us. Let's take a closer look at the most important branches of civil engineering and what they do. 1. Structural engineering. Imagine designing a skyscraper that can stand tall during an earthquake or a bridge that can hold the weight of thousands of cars. That's the job of structural engineers. They figure out how to make buildings and structures strong, stable, and safe. They also choose the right materials like steel or concrete to handle the forces acting on a structure. 2. Geotechnical engineering. Ever wonder what's under building? Geotechnical engineers study the soil and rocks beneath our feet. They make sure that the ground can support structures like buildings, dams, or tunnels. Without their expertise, a building could sink or collapse over time. 3. Transportation engineering. From highways to airports, transportation engineers make it easier for people and goods to move around. They design roads, railways, and traffic systems to keep everything running smoothly and safely. Think of them as the planners of how we travel. 4. Water resources engineering. Water is one of our most important resources. Water resource engineers work on projects like dams, canals, and drainage systems to manage and distribute water. They also help prevent flooding and ensure clean drinking water for communities. 5. Environmental engineering. This branch focuses on protecting the environment. Environmental engineers design systems to reduce pollution, clean wastewater, and recycle materials. Their work helps keep the air, water, and land safe for everyone. 6. Construction management. While other engineers design structures, construction managers oversee the building process. They plan schedules, manage budgets, and make sure everything is built according to the design. Each branch is important, and many civil engineers specialize in one or more of these areas. Understanding these branches will help you decide which part of civil engineering excites you the most. Page 4. The basics of forces and loads. Civil engineers must understand forces and loads because every structure must withstand them. Let's break this down into simple terms. What are forces? Forces are pushes and pulls that act on a structure. Here are the main types of forces. 1. Compression, push. Oh, imagine squishing a sponge between your hands. The force pushing inward is called compression. Columns in buildings handle this type of force. 2. Tension, pull. Oh, think of pulling a rubber band. The force pulling it apart is called tension. Cables on suspension bridges, like the Golden Gate Bridge, handle tension. 3. Shear, sliding. Oh, imagine sliding one half of a piece of paper one way and the other half the opposite way. This sliding force is called shear. It happens in bolts or beams under pressure. 4. Bending. Oh, picture a diving board bending when someone stands on it. This force happens in beams and needs to be controlled to avoid breaking. 5. Torsion, twisting. Oh, twisting a wet towel creates torsion. It's common in things like shafts or bridges exposed to strong winds. What are loads? Loads are the weights or forces that a structure must carry. There are 3 main types. 1. Dead loads. Oh, these are the weights of the structure itself, like the walls, floors, and roof. They don't change over time. 2. Live loads. Oh, these are temporary weights, like people walking in a building or cars on a bridge. Engineers must plan for these loads to vary. 3. Environmental loads. Oh, these come from nature, like wind loads, how strong wind pushes on a building. Snow loads, the weight of snow on a roof. Earthquake loads, shaking forces that can cause buildings to sway. Why are forces and loads important? If engineers don't plan for these forces and loads, buildings can crack, bend, or even collapse. Knowing how to calculate and manage these forces is one of the most important skills a civil engineer has. Page 5. The strength of materials. Civil engineers work with different materials to build safe and strong structures. Choosing the right material depends on its strength, durability, and cost. Let's explore the most common materials used in civil engineering. 1. Steel. What is it? Steel is a super strong metal made from iron and carbon. Why is it great? Oh, it can handle both compression, push, and tension, pull very well. Oh, it's flexible enough to bend slightly without breaking, which is helpful in earthquakes. Where is it used? Oh, skyscrapers, bridges, and reinforced concrete. 2. Concrete. What is it? Concrete is a mixture of cement, sand, gravel, and water that hardens over time. Why is it great? Oh, it's strong in compression but weak in tension unless reinforced with steel. Oh, it lasts a long time and resists weathering. Where is it used? Oh, foundations, walls, and bridges. 3. Wood. What is it? Wood comes from trees and has been used for building for thousands of years. Why is it great? Oh, it's lightweight, easy to work with, and affordable. Oh, it can handle tension and compression fairly well. Where is it used? Oh, homes, smaller buildings, and temporary structures. 4. Brick and stone. What is it? Bricks are small blocks made from clay, and stones are natural materials like granite or limestone. Why is it great? Oh, they are very durable and strong in compression. Oh, they look great for aesthetic designs. Where is it used? Oh, walls, arches, and decorative features. 5. Glass. What is it? Glass is made from sand and other materials melted together. Why is it great? Oh, it's transparent and can add beauty to a structure. Oh, modern glass can be strong and even bulletproof. Where is it used? Oh, windows, facades, and greenhouses. 6. Composites. What is it? Composites are materials made by combining 2 or more other materials. Oh, example, fiber-reinforced plastic, FRP. Why is it great? Oh, it's lightweight and strong, often used for specific needs like high-tech bridges or boats. Where is it used? Oh, specialty projects like modern bridges or unique architectural designs. Why do engineers care about materials? Every material has strengths and weaknesses. Engineers must 1. Understand the forces the material will face. 2. Pick the right material for the job. 3. Make sure the material can handle weather, wear, and time. By knowing your materials, you can make buildings, bridges, and roads that last for decades or even centuries. Page 6. Foundations, the base of every structure. Every structure needs a strong foundation. Without one, it could sink, crack, or even collapse. A foundation is the part of a building that connects it to the ground and supports its weight. Let's break down the basics. 1. Why do foundations matter? Imagine trying to build a tower of blocks on soft sand. It would fall over, right? Foundations spread the weight of the structure evenly so that it doesn't sink or tip. They also protect the structure from shifting due to soil movement or earthquakes. 2. Types of foundations. There are two main types of foundations, shallow and deep. A. Shallow foundations. What are they? Foundations that are close to the surface of the ground. When are they used? Oh, for small buildings or structures on hard, stable soil. Examples. Oh, spread footing, a flat concrete pad that spreads the weight of a column or wall over a large area. Oh, slab on grade, a thick concrete slab that acts as both the floor and the foundation, often used in homes. B. Deep foundations. What are they? Foundations that go deep into the ground, often using long poles or piles. When are they used? Oh, for tall buildings, heavy structures, or soft, unstable soil. Examples. Oh, piles, long poles made of wood, steel, or concrete driven deep into the ground. Oh, caissons, large concrete cylinders that are sunk into the ground for bridges or towers. 3. Soil and foundations. Not all soil is the same, and it affects how a foundation is built. Here are some common types of soil. Rock, great for foundations because it's hard and stable. Sand, tricky because it can shift, needs deep foundations. Clay, expands and shrinks with water, which can crack foundations. Silt, weak and slippery, needs special care. 4. How do engineers test the ground? Before building, engineers study the soil by soil borings, taking samples from deep underground. Load tests, checking how much weight the soil can handle. Water table studies, finding out how close groundwater is to the surface. 5. Challenges in foundations. Foundations must deal with uneven soil. Some parts of the ground are stronger than others. Settling. Over time, soil might compress, making the structure sink slightly. Earthquakes. Foundations must keep the building stable during shaking. Why foundations are critical. A strong foundation ensures that the structure stays safe and stable for decades. It's the first step in any construction project, and without it, even the best designed buildings can fail. Page 7. Beams, columns, and the skeleton of a structure. The skeleton of a building or bridge is made up of beams and columns. These are the basic parts that hold up the structure and keep it standing. Let's explore how they work together. 1. What are beams? Definition. Beams are horizontal pieces that carry the weight of floors, ceilings, or roofs and transfer that weight to the columns or walls. What do they do? O. Spread weight evenly across a building. O. Handle forces like bending when the middle of the beam sags under weight. 2. What are columns? Definition. Columns are vertical supports that carry weight from the beams and transfer it to the foundation. What do they do? O. Handle compression, pushing force from the structure above. O. Keep the structure tall and stable. 3. How do beams and columns work together? Beams and columns form a frame, like the skeleton of a body. The columns carry the vertical weight, gravity, while the beams distribute loads horizontally. Together, they make sure the structure doesn't bend, twist, or collapse under its own weight or external forces. 4. Types of beams. 1. Simply supported beam. O. Supported at both ends, like a plank across two chairs. O. Common in small bridges or basic floor systems. 2. Cantilever beam. O. Supported at one end only, like a diving board. O. Used in balconies or overhanging parts of buildings. 3. Fixed beam. O. Fixed at both ends, making it stronger and more stable. O. Used in high-rise buildings or large bridges. 4. Continuous beam. O. Supported at multiple points along its length. O. Common in long-span bridges. 5. Types of columns. 1. Short column. O. Handles heavy compression without bending. O. Used in shorter buildings or ground-level support. 2. Slender column. O. Taller and thinner, but can buckle under heavy loads if not designed properly. O. Found in taller buildings or open spaces. 3. Tied column. O. Has reinforcing steel bars tied together for extra strength. O. Common in concrete structures. 4. Spiral column. O. Reinforced with steel arranged in a spiral shape, making it resistant to buckling. O. Used in earthquake-prone areas. 6. Materials for beams and columns. Steel. Strong and can handle bending and compression well. Concrete. Often used for columns and beams, especially when reinforced with steel. Wood. Used in smaller structures like houses. 7. Why beams and columns are important. Without beams and columns, a structure would collapse like a house of cards. They act as the framework that holds everything together. Civil engineers must calculate the right size, material, and placement to make sure the structure is safe and efficient. Page 8. Loads. What every structure must handle. Every structure has to carry loads, which are the forces or weights acting on it. Civil engineers carefully calculate these loads to ensure the structure stays safe and stable.
Let's break them down step by step.
1. Types of loads. A. Dead loads. What are they? O. These are the permanent, unchanging weights of the structure itself. For example, the walls, floors, roof, and beams. Why are they important? O. Engineers must account for these loads because they're always there, even when no one is using the building. B. Live loads. What are they? O. These are temporary weights that change over time. For example, people walking in a building, furniture in a room, cars driving on a bridge. Why are they important? O. Engineers plan for the maximum possible live load to avoid overloading the structure. C. Environmental loads. What are they? O. These come from nature and can be unpredictable. Common examples include wind loads, the force of wind pushing against a building or bridge. Snow loads, the weight of snow or ice on a roof. Earthquake loads, shaking forces during an earthquake. Flood loads, water pressure from floods or rising groundwater. 2. Load combinations. In real life, structures face more than one load at a time. For example, a bridge might carry live loads, cars, while also dealing with wind loads. Engineers create worst-case scenarios by combining loads to make sure the structure can handle them all at once. 3. How do engineers calculate loads? 1. Measurements. Engineers measure the weight of materials, e.g., how heavy a steel beam is. 2. Code requirements. Building codes provide guidelines for typical live and environmental loads in specific areas, e.g., snow loads in snowy regions. 3. Safety factors. Engineers add extra strength to account for unexpected events. 4. Examples of loads in action. Bridge example. A bridge must hold the weight of cars, live load, while also dealing with wind pushing against it, wind load. Skyscraper example. A tall building must handle wind loads at the top, live loads from people and furniture, and dead loads from its materials. 5. What happens if loads are miscalculated? Miscalculating loads can lead to O. Cracks or sagging. Parts of the structure weaken over time. O. Collapse. In extreme cases, the entire structure can fail, causing loss of life and property. 6. Why load planning is critical. Accurately calculating loads ensures that structures stay safe for decades. It's one of the most important responsibilities of a civil engineer and involves a mix of science, creativity, and foresight. Page 9. Tools and technology in civil engineering. Modern civil engineers rely on advanced tools and technologies to design, analyze, and build structures. These tools make work faster, more accurate, and allow for the creation of complex projects. Let's dive into the essential ones. 1. Design software. Design software helps engineers create blueprints, test ideas, and visualize projects. AutoCAD. What is it? A drafting tool used to draw precise 2D and 3D designs. What is it used for? Creating detailed plans for buildings, bridges, and roads. Drawing layouts for utilities like plumbing or electrical systems. Revit, BIM, building information modeling. What is it? A software that allows engineers to create 3D models of a structure. Why is it important? It helps visualize the entire project before construction. Engineers can coordinate designs with architects and other specialists. See SAP 2000 and tabs. What are they? Tools used for structural analysis. Why are they used? To test if a design is strong enough to handle loads like wind, earthquakes, or heavy traffic. 2. Surveying tools. Before construction begins, engineers need to measure the land. Surveying tools help ensure the structure is built in the right location and level. Total station. What is it? A device that measures distances, angles, and elevations. Why is it important? It's used to map out the land accurately and align structures perfectly. GPS, Global Positioning System. What is it? A satellite-based tool that provides location data. Why is it used? For large-scale projects like roads or pipelines where precise positioning is critical. Underscore 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 underscore. 3. Construction technology. Technology on construction sites helps manage and execute projects. Drones. What are they? Flying cameras that can take aerial photos and videos. How are they used? Inspecting hard-to-reach places. Monitoring progress on large construction sites. 3D printers. What are they? Machines that create physical models from digital designs. Why are they used? To create prototypes or even build small-scale structures layer by layer. 4. Testing and monitoring tools. Civil engineers test materials and monitor structures to ensure safety. Compression testing machine. What is it? A tool that tests how much force a material can handle before breaking. Why is it important? It's used to check the strength of concrete, steel, or other materials. Sensors. What are they? Devices that measure stress, vibration, or temperature. How are they used? To monitor bridges, skyscrapers, and dams for signs of wear or damage. 5. Collaboration platforms. Engineers often work with large teams. Collaboration tools make communication easier. Examples: Autodesk BIM 360, Procore, or Microsoft Teams for sharing designs, schedules, and updates. Why tools matter. These tools save time, reduce errors, and allow engineers to work on ambitious projects that were once impossible. Mastering these technologies is essential for any high-level civil engineer. Page 10. Building codes and regulations. Every civil engineering project must follow strict rules to ensure safety, reliability, and environmental protection. These rules are called building codes and regulations. Let's explore what they are and why they're so important. 1. What are building codes? Definition. Building codes are a set of laws and standards that dictate how structures should be designed, built, and maintained. Purpose. To keep buildings safe for people to use. To ensure structures can handle natural forces like earthquakes or high winds. To protect the environment by limiting pollution or waste. 2. Why do we need building codes? Without building codes, buildings might collapse under heavy loads. Fires could spread quickly due to poor design. Roads and bridges might fail, causing accidents. Construction could harm the environment. 3. Who sets the codes? Building codes are created by government agencies and professional organizations. Examples include International Building Code, IBC, a global standard for safety and design. American Concrete Institute, ACI, sets rules for concrete structures. American Society of Civil Engineers, ASC, provides guidelines for loads, wind resistance, and more. Local governments adapt codes to fit specific climates and needs, e.g., snow in cold areas, hurricanes in coastal areas. 4. Key areas covered by building codes. 1. Structural safety. O ensures buildings can handle loads and natural forces. O requires materials like steel and concrete to meet strength standards. 2. Fire safety. O regulates fire exits, sprinklers, and fireproof materials. O ensures people can escape safely during emergencies. 3. Accessibility. O requires features like ramps and elevators for people with disabilities. 4. Energy efficiency. O promotes the use of insulation, energy-efficient windows, and renewable energy sources. 5. Environmental impact. O limits pollution and waste during construction. O protects natural resources like water and forests. 5. How do engineers follow building codes? Step 1. Study the codes. Engineers review all relevant codes before starting a project. Step 2. Design according to standards. Plans are created to meet the requirements. Step 3. Submit for approval. Designs are sent to government officials for review. Step 4. Inspections. Inspectors check during and after construction to ensure compliance. 6. Consequences of ignoring codes. If engineers don't follow building codes, the project could be shut down by authorities. The structure might fail, leading to injuries or deaths. The company could face fines or lawsuits. Why building codes are essential. Building codes aren't just rules. They're a promise that structures will be safe, reliable, and environmentally responsible. Understanding and applying them is one of the most important responsibilities of a civil engineer.